Here's a video for Unit 5, Part 1B, Solving Systems of Equations by Substitution. So, as a starter question, I want you to think about, in math, what does it mean to substitute? So hopefully we all associate the word substitute with to plug in, right? When we substitute a number, we plug it into the equation. Now, what are we plugging it in for? Well, when you substitute, the thing that you are substituting in must be of equal value. Okay, so you can make any type of substitution between any two things that are equal in math, and that's something we're going to use today for solving systems of equations. So now this is going to be our first algebraic method. So we did already talk about solving systems graphically, which is not considered an algebraic method. So if you ever see a direction that says solve this algebraically, this is one of the methods you can use. So to do so, again, we have to make sure we are substituting something. So what are we substituting? Well, if we take a look at the second equation, we can see here that x is equal to this entire expression 2y minus 13, which means any place I see an x, I can plug in 2y minus 13. So where are we going to substitute it? Well, we need to make sure when we're working with systems of equations that we use both equations. So if we're substituting from the second equation, we must plug it into the first equation. So I can rewrite this first equation as 2 times and replace my x with 2y minus 13. Everything else can follow. Okay, so we are just replacing my x with this expression right here. Now the rest is regular algebra. I'm going to distribute the 2 to the parentheses, so I get 4y minus 26 is plus y is equal to -1. We combine our like terms. 5y minus 26 is equal to -1, and we isolate our variable. 5y equals 25, divide by 5 on both sides. Y is equal to 5. Okay, so by this substitution, we were able to turn an equation from 2 variables over here into an equation with 1 variable over here and solved for that variable. Now remember, a solution has to make an equation true. So in order to make any of these equations true, we need a value for both x and y. So we're going to do a second substitution. We're going to take this value of y and substitute it into one of the equations. Technically, it does not matter which one we use, okay, to find the value of x. Now, I'm going to choose the second equation because it's already solved for x. And I'm going to plug in the 5 for y. So I get x is equal to 10 minus 13. So my x is equal to -3. So now that I have a value for both x and y, I have the complete solution. X is equal to -3, y is equal to 5. We can write this as an ordered pair, -3, 5. Now it also says to check. Now remember, in order to check my solutions, it has to be a solution to both equations. So when I do my check, I'm going to check both equations. So number 1, 2 times my x value, which is -3, plus my y value, which is 5, is equal to -1. So 2 times -3 is -6. -1 equals -1. Checks out. Check the second equation. My x value, which is -3, has to be equal to 2 times my y value, which is 5, minus 13. So -3 is equal to 10 minus 13. -3 is equal to -3. Check. Okay? So again, it's just going to be a series of substituting things into equations until we find both variable answers. So let's try a second example. So first ask yourself, how is this example different from the first one? Well, it's different because in the first one, one of my variables was already solved for, the x. In this example, neither variable is solved for in either of the equations, so we have to solve for one in order to be able to substitute it into the other. So there's going to be a clear choice here. You want to solve for the variable that's easiest. Well, what's easiest? Any variable that does not have a coefficient is going to be much easier to solve for than a variable that has a coefficient, because when you go to divide on both sides, you can create fractions, whereas if there's a 1 here, you don't. Okay, so I'm going to solve for y in that second equation. Two x plus 4. Okay, so now that I've solved for one of my variables, I'm going to follow the rest of the steps. I know y is equal to this entire expression, so I've already used equation 2. Now I have to make sure I plug that into equation 1. So 3x plus 3 times the substitution for y, which is 2x plus 4, has to be equal to 1. So we distribute 3x plus 6x plus 12. 9x plus 12 is equal to 1. Now you'll notice here that my answer is going to be a fraction. And that's okay. We are allowed to get fractions as answers. So when we substitute, we're going to substitute the fraction equivalent. Okay, so I have my x value. I'm going to find my y value. Now, I know I've already solved for y in this equation over here, so I'm going to continue with this equation. 2 times negative 11 over 9 plus 4. This is something you can plug into your calculators, and when you do, you'll get y is equal to 14 over 9. Okay, so my answer is x is equal to negative 11 over 9, y is equal to 14 over 9, or as an ordered pair, negative 11 over 9, comma 14 over 9. I am going to ask that you check on your own in your own notes to make sure that answer works out. All right, so that's the basics behind this. Now, there are some unique cases that can occur. Okay, so you won't know it's a unique case until you're in the process of solving it. So the directions just tell me solve the system by substitution. So I'm just going to follow the rules that I know, which is one of my variables solved for? Yes. Can I substitute that into the other equation? Yes. So I'm going to take this 4/3 x minus 7 and plug it in for y into the first equation. 4x minus 3 times 4 over 3x minus 7 equal to 15. We distribute 4x. Now remember, when you distribute to the 4/3, the 3's should cancel out, leaving me with negative 4x. And negative 3 times negative 7 is a plus 21. Now you should notice something interesting happening here. 4x minus 4x, when we go to combine those like terms, actually cancel out. And we end up with the equation 21 is equal to 15. Well, we should recognize that 21 isn't equal to 15. There's no way possible. So this is a false statement. Okay? It's not true. Which means that no matter what value for x I'm going to plug in, we're not going to get a true statement. So whenever I see something like that, I need to tell how many solutions I have. In this case, there are no solutions. Okay, and there are no solutions because it is a false statement. Now, if you remember from graphing, that means that these lines are going to be parallel. Okay, which means they have no points of intersection. And if you actually solve for y equals mx plus b form in both, you'll notice they'll have the same slope and different y-intercepts. Okay, so again, false statement means no solutions. And we continue. Solve this system by substitution. Another unique case. Okay, is one of my variables solved for? Yes. Let's plug it into the other equation. So that's x plus 2 times negative 1/2 x plus 4 is equal to 8. We distribute x plus, oh wait, when I distribute that 2, I get a negative 1x plus 8 is equal to 8. So again, we have that situation when we go to combine our like terms, the x's are going to cancel out. But this time, they cancel out and we get 8 is equal to 8, which is a true statement. Which means no matter what values for x I plug in, I will always get a true statement. That means that I have infinitely many solutions. So if you were to compare this to the graph, you would see that these are coinciding lines, that they are two lines that are directly on top of each other. And if you solve for y equals mx plus b form, you'll see that they have the same slope and the same y-intercept. So again, true statement means infinitely many solutions, and you need to make that declaration, right? Because it's asking you to solve. So 8 equals 8 is not a solution. Infinitely many solutions is the answer we're looking for. So in conclusion, if you're a person who likes steps, here you go. When we're solving linear systems by substitution, the first thing you want to do is solve one of the equations for one of its variables. If it's already solved, you can proceed to step 2. Step 2 says substitute the expression from step 1 into the other equation and solve for the variable. So that's what we did here, right? We took this value, this expression, and substituted it into the second equation and solved. Now, obviously, if we have a true statement or false statement, we know no solutions or infinitely many solutions. But if we get a value, we're going to take that value and plug that back into the equation you have already manipulated. And again, that's just to make your life a little bit easier. And finally, you want to check the solutions, whether you check that graphically or you check that by plugging in. You always want to make sure that you are double checking your answers. So now we're going to have a number of methods for solving this. Obviously, graphing is one, substitution is the second. So when should we use the substitution method? Well, first, if we see algebraically written, we know this is a possibility that we can use this method. And it's easiest to use when one of the variables is already isolated, like we saw in a couple of the examples, or when the coefficient of one of the variables is 1 or -1. You'll see that if the coefficients are not 1 or -1, you'll have to start doing some dividing, and you might end up with some messy fractions. So to avoid that, we will have another method for us to use on a later date. Okay, so we're trying to avoid the extra fractions. So I'm going to ask that you pause the video at this moment to try and attempt this by substitution. And I will show you the answers in a little bit. Okay, so here's the solution. You want to solve for one of the variables. I chose this -y because it doesn't have a numerical coefficient that's not 1 or -1. And that's done over here, and you can follow my arrows. So that was step 1. I took that, plugged it into step 2, found that x was equal to 2, and plugged that back in to find y was equal to 1, and I have my check over here.